Hi there. So in this video I'm going to run through how to use Bezier splines to fit unknown curves through a set of prescribed points. And what I mean by unknown is that you have a set of coordinates, or for this example, this video, we're going to use two-dimensional points, and basically you want to join them up smoothly, but you don't necessarily know the functional form of these points, so you can't use standard fitting procedures. So a Bezier spline, or B-Spline for short, is actually generally used in computer graphics, and what it does, it's basically you have a set of points which describe, for example, the edge of an object, and you'll use a B-Spline to join up the points smoothly so that you can get sort of curved effects without having to have horrendous numbers of polygons in your computer rendering. So here, for example, we have some coordinates, just two-dimensional coordinates in x and y, and if you were to fit a B-Spline through all these, you'll get something like this. So this is actually using what's called a cubic spline, and that's what I'm going to focus on for this video. And the important point here is that this Bezier spline goes through the points. There's a lot of information out there on how to get a Bezier spline to sort of weave between points, and that's often what's used in computer graphics. But there are certain times when you want it to go through all the points, and that's actually slightly more complicated. So this video is pretty involved, but the results are very, very useful indeed. So how would you use this in science? So just an example, consider the following situation. If you're an experimentalist and you have some sort of piece of apparatus which outputs radiation, for example, at a certain power, and you control it with a computer using a voltage source, so you provide a voltage input into this piece of equipment and it will produce an output in some sort of radiation with a certain power. What you would do, you would calibrate that equipment, so you can just use your computer program to send voltages into your piece of equipment. However, what could happen is there could be a relationship between the voltage and the power, which is not necessarily straightforward. And certainly importantly, it may not have a functional form, especially if it's a complicated piece of equipment. So what you want to do, if you want to be able to calibrate the piece of equipment efficiently without having to take millions of data points, so you can use any voltage to get any power accurately, you can't just fit a curve to it because you don't know the functional form. So basically what we want to know is how you would get an arbitrary power from a voltage using this. So what we could do, we could use Bezier splines and fit every point using a cubic Bezier spline. So although it's perhaps not perfectly accurate, it's a sort of a smooth relationship rather than drawing straight lines between these points, which arguably isn't quite as accurate. So this is just for some data where you don't know the functional form, and in this case we'll draw a spline that looks like the following. Okay, so how do we do this? This is actually quite an involved process, and like I say, it is rather time consuming to get it all working, but once you've got it sorted, it can be very, very useful indeed. So the first thing you do is get your known points, your specified points. So in our case, it's some voltage and some power output, and I've just used volts and milliamps. And then what we're going to have to do is take these values and put them into a matrix. The next thing is once we have these points, the next thing to do is evaluate what's called the C matrix. And I'll come to what this is later, but basically you just have to create a matrix which has two less rows than our original set of points and carry out some algebra, and we'll get some useful values in this matrix, which is one step towards the final result. One useful thing we need to know is what's called the 1-4-1 matrix. This is just using the algebra to evaluate what's called a control points. And depending on the size of your data, the 1-4-1 matrix will vary in size, but it always has this sort of functional form where the diagonals are all 4 and the positions adjacent to diagonals are 1 and the rest of the positions are 0. One thing we'll need to do is invert the 1-4-1 matrix as part of our algebra, and I've made another video that explains how to invert an arbitrary square matrix, which you can watch if you're unfamiliar with matrix inversion. Then we'll also have to evaluate what's called the control points. So basically in that case, we'll create a matrix which has the same dimensions as our original set of data points, but the values within it are different. And we evaluate these values using a combination of the C matrix, the original specified points and the 1, 4, 1 matrix, or more accurately, the inverse of the 1, 4, 1 matrix. And once we have this set of control points, labeled B, we can then create our splines. So each of the splines we're going to create has 4 points. So to actually have a spline which covers a large set of data points, you'll need to create a spline between each of these points. And each of these individual splines between the 2 points is controlled by 4 points. And finally, we'll just quickly run through how to evaluate the spline and to get positions between 2 data points at any arbitrary position between them. Okay, so the first thing we need to do is get our original data points. So these, for example, if you're carrying out an experiment, will be your calibration points. You've applied a voltage and you measured the power for a certain number of positions, but you can't do it for all, of course. So once we have these values, we tabulate them, and then we just put them into a matrix. And the dimensions of the matrix are basically the same size as our table. So we have 2 positions, and like I say, for this video, we're just going to be looking at 2-dimensional data. And we have 6 data points, so we're going to have a 6 by 2 matrix, as seen here. So we just put the values into the matrix as follows. And when we want to address a certain position or a certain pair of values, we just do it as the following. So we have a single line under our S to indicate it's a vector rather than a matrix, and we index it with the I there, which corresponds to the row in the matrix. So for example, if we're interested in the third data point, S3, you'd address elements S31 and S32 within the matrix. And they of course are 10 and 16.8. Okay, so next thing is to evaluate the C matrix. So we have a set of data points, which are n by m dimensions. In case that's 2 by 6, and we need to create what's called the C matrix. So the C matrix, as I mentioned earlier, has the same number of columns as the original set of data, but it has 2 less rows, and that will become clear why that is the case very shortly. So in our case, we have n times n minus 2, which of course is 2 times 4. So when it comes to evaluating our C matrix, the values of S which go into the matrix are as follows. So the top line C11 and C12 is dependent on the first 2 columns of the S matrix, and the bottom row of the C matrix is dependent on the bottom 2 rows of the S matrix, and then there's a one-to-one correspondence between all the other elements, all the other rows, sorry. So what exactly is the C matrix? So I'll run through how you evaluate it. For this video, like I say, there are quite a lot of details in carrying out this sort of analysis and evaluating these Bezier splines. So I'm not really going to go into why you do it. There is literature out there, but basically the purpose of these videos, and this one's no exception, is basically to give you a technique and how to do it. And if you want to work out more about the inner workings of this or adapt it, then perhaps you will have to go away and dig a little bit deeper. But for this video, I'm just going to run through and do it step by step exactly how you do this. And then, for a lot of people, that is perhaps adequate. If you don't really care about the details of Bezier splines, you just want to use this as a tool for the other parts of your work. Okay, so we're going to take these rows out to be vectors, 2-component vectors, which are just corresponding to a voltage and a power for the first and second columns respectively. So for the first row, C1, the value of it is going to be equal to 6 times the second row of the S matrix minus 1 times the first row. For the last row, it's a similar situation. It's going to be 6 times the m plus 1 row, and you take away from that the single 1 times S times the m plus 2 row. The m here refers to the C matrix, so these are m plus 1 refers to, for example, in our case, the 5th row, and m plus 2 refers to the 6th row, which of course exist within the S matrix, but don't within the C matrix. So these, just to be clear, these subscripts are corresponding to the C matrix. And then for every other element, it's just the ith row of the C matrix is equal to 6 times the I plus 1 row of the S matrix. So you just shift all the rows down slightly by 1. Okay, so just as an example, the row C2 will be equal to 6 times S3. And if you were to evaluate both the elements, it's just as follows, which is relatively straightforward. So let's do that in our case. We have the S matrix here, and let's start with the first row. It's 6 times S2 minus 1 times S1. So it's just as follows. And then for the second and third rows, we use the else condition. So that's basically 6 times the row above the position within our C matrix. So for the second row, that would be the third row in the S matrix. And for the third row in the C matrix, it will be the fourth row in the S matrix. And then we get to the final row, which is just, as I said before, 6 times the m plus 1 row in the S matrix, and you subtract from that the m plus 2 row of the S matrix. Okay, so here we have the C matrix evaluated for in terms of S. We have some real data for S, so we can just plug these values in and carry out the algebra. It's all relatively straightforward, but I'm just going to run through it anyway. You can pause the video just to check if you want to make sure how all this works, but I'm just going to run through it reasonably quickly. And there we have it, that's our C matrix evaluated. So that's step 2 complete. And there it is. Okay, so the next step is to evaluate what's called the 1-4-1 matrix. As I mentioned before, this is just a specified matrix which is used in the algebra of this process. What you should note is the only important thing is to determine the dimensions of the matrix. So we have a 2x4 matrix, we have 4 rows, and we're going to do some algebra. So it turns out basically you need the M matrix, which is just the label we're going to use for the 1-4-1 matrix, to be equal, it has to be a square matrix because we're going to invert it. It has to be equal to M times M. So in our case there are 4 rows, so the matrix, the 1-4-1 matrix will be a 4x4 matrix. And as I said before, the diagonals within the matrix are set equal to 4. Positions adjacent to the diagonals are all set equal to 1. And all the other positions are set equal to 0. And depending on the number of data points you have, your matrix may be smaller or almost certainly will be larger. Okay, so the next step is to invert the 1-4-1 matrix. For the purpose of this video, I've just carried out the inversion and given the answer, which is this matrix on the right hand side. As I said before, you can go to my other video, which is linked here, and you can see exactly how to carry out matrix inversion if you're unfamiliar with doing that. It's a little bit involved, but it has to be done. Okay, so the 5th step, this is evaluate the control points. So we have a 2x6 matrix containing all the data points that we started with, and what we need to do is create what's called the control points for our matrix, for our Bezier splines, and we label these with the letter B. And the dimensions of this matrix are exactly the same. There are points, basically there's a 1-to-1 correspondence between the points in the S matrix and the B matrix, but we have to do some algebra to arrive at these values. So how do we do that? Okay, so this is again reasonably involved, or not necessarily involved, but it's it's a reasonably unintuitive. So like I said before, if you really want to know more about Bezier curves and so on, you have to look into the literature. I'm just going to describe how you get the B matrix step by step. So the way it works is the endpoints are the same, and you can sort of see when you look at the graph why that's the case, because our spline that goes through all of our data points will start and end at these endpoints, and that turns out to be important for when it comes to Bezier spline fitting. So these endpoints are set, so it's just the other 4 values in the middle which we need to determine. And that is where the C matrix comes in. So we use the remaining points. In the center will be filled with values which are determined using the C points. We don't just take the C points, we have to do a little bit of algebra to get them, but it is these points which are used. And just for the sake of the video, I'm just going to use B tilde to illustrate a matrix for the points which go into the middle of the B matrix. So how do we evaluate the B matrix? Well, it's just using the two matrices we've already evaluated. So we need to multiply the inverse of the M matrix, that's the inverse of the 1, 4, 1 matrix. We need to multiply that by the C matrix that we've evaluated, and that will give us all these B tilde points. So that's just as follows, and we have all the values evaluated before, and I'm not going to run through all the matrix multiplication, but it turns out the result is as follows. So this is the B tilde matrix. It looks like they're large numbers, but obviously there's a factor of 2090 out the front there, so they're all between 1 and 20, most of these values. Okay, so we have the B tilde matrix, and what do we do with it? We basically just put all these values back into our original B matrix as follows. So this is how we do it. So basically you're just shifting down the rows. So for example, the row 2 in the B matrix is equal to row 1 in the B tilde matrix, and as follows. So it's reasonably straightforward just to fill those points in. And that's the whole matrix evaluated for the data we have. Okay, so that's the control points, that's our B matrix. Now we have to move on to step 6, which is okay, so we now come on to step 6, which is the most involved part of the process, and this is where we create the splines. So basically between each of the pairs of data points that we have to create a spline between them. So really, in essence, we're creating multiple splines rather than just one large one. So each of these splines is made up of 4 points. So each point has 2 positions, or in our case we're using data, so it's a voltage and a power. So basically we have a matrix. So for each of these splines it will be a 2x4 matrix, and that is not specific to this example. Each spline, whatever you're doing, will always have 4 points, and each of these points will of course have two positions or 2 elements, whatever. Okay, so basically you notice we have a superscript here, I. So like I said, you need to have a spline for each of the pairs of data points, or a spline between each pair of data points in your data. The question is, how many splines do we need? Well, original data in our case is 6 elements, so we have 6 rows in our matrix, corresponding to the 6 data points we have. But if you look at the data and count the lines between them, there are 5. So of course there's 1 less row in our matrix, or not in our matrix, sorry, we have 1 less spline than we have data points. So the answer is, in all cases, m-1 splines, because of course you need 2 data points per spline. So rather than try and draw a rank-free tensor, I'm just going to have an array of matrices. Is the easiest way, I think, to visualize this and express it. So in our case we have 6 data points, so we have 5 splines, and each of them are labeled with this superscript I. Okay, so let's start with spline 1 and let's evaluate this. So we need to know the 4 points in our spline before we can use it. Okay, so we have our data, and we're looking at spline 1, which is between the first 2 data points. So if you look at that, we need to know the positions that are used in this spline. Well, we know the endpoints already because these are specified by the data points originally, and we have the first position there, which is position 1 in our experimental data, and we have position 2. So this is the first row and the 4th row are straightforward. We can just copy there, and we can copy the 2nd row into the 4th row of our line. But what about the middle 2? So this is a little bit more complicated, and once again I'm following the philosophy where I'm not going to tell you why, I'm just going to tell you how to do it. And it turns out this is where the B matrix comes in. And we don't just take the points from the B matrix, we have to do a little bit of algebra, but it's pretty straightforward. So the way you do it, we're going to take them out and just look at them as vectors rather than elements of a matrix. And it's basically as follows. You take out the two components, and then we work out the difference between them. We're going to call this delta B. So it's just B2 minus B1. Then we're going to take 1/3 of delta B and 2/3 of delta B, which is equal to the following if you evaluate both terms within the vector. And then we're going to add B1 to these. And that's what you get. So these actually are the elements within our matrix. Like I say, the actual details are, it's reasonably involved, but it turns out what you're trying to do is you draw a line between these control points, and then you basically want to take the positions 2/3 and 1/3 of the way between these points. So that's what you're doing there. But for the case of just executing this to use it, we're just going to take the values. So what you do, using B11, B12, B21, and B22, you just substitute into the matrix as follows. And this is not specific to this example, this is general. So as long as you just know this, this will always work. Okay, so that's how you do it. And this is our first spline. Okay, so these are the control points. So these are the points within the spline, and we have all of them now. We know all of these values. I'm not going to evaluate the numbers because it'll just get very messy, but you can do it. And it's not particularly computationally intensive. The only thing that's tricky is the matrix inversion, and that's if you have a large data set. Okay, so that's spline 1. Let's have another look at a different spline. Let's look at the second one. Okay, so you notice the superscript here will change from 1 to 2. That's the only difference. Once again, as always, the spline contains 4 elements. And we use the S matrix. Look at our data. Now we're looking at the second spline here. That's the one we're interested in. Let's zoom in on that. And in this case, the 2 points at the ends are the second row and the third row. So the second row is the first point, and the third row is our second point. So taking these values from the S matrix, in this case, for the second spline, we start at the position S2, row 2, sorry, and we end at row 3. Okay, so then the B matrix, and once again, because this is the second spline, we're looking at positions 2 and 3 rather than 1 and 2, as was the case for the first spline. And then we just substitute in. And it's exactly the same process, the maths is the same, you just substitute in these values, and that is your spline. So that's spline 2, and then you can go through and continue that process to fill up every one of the splines. And we can write this down as a general equation, which is perhaps more useful when it comes to memorizing all this sort of stuff. So basically for spline I, that's out of m minus 1, where m is the maximum number of rows, is the number of rows in the S matrix. Basically the top 2 elements are SI1 and SI2, and the last elements are SI plus 1, 1 and SI plus 1, 2. And then the B matrix is used to fill in the middle 2 rows, and again you use the same positions within these matrices. Okay, so that's the general equation. Finally, step 7, evaluating the spline. So this is actually a reasonably straightforward part of it, and what we do, we use this equation here. Generally in the literature this is termed B, capital B on the left hand side there, but we've already used B, so I'm just going to call it R. And what this is a cubic equation, and basically you have a parameter t which you enter into this equation, and that will affect the prefactors which are placed in front of our 4 points. So basically what we're doing, the position of interest is some sort of mixture of the 4 points in our cubic spline. So that's why we evaluated these 4 points, and depending on if you go from 0, that will be entirely P1, and you go to 1, that's entirely P4, and as you go between 0 and 1, and it can be any number between 0 and 1 inclusive, you'll get some mixture of these points, and that's the way the spline works. Okay, let's take an example. So how do we evaluate our spline? So we start off with basically nothing, and the first thing we do is we get our spline. So we're just going to evaluate spline 1. The process is the same for all of them. We have our spline, we know all of the elements of our matrix, and the endpoints of our spline are determined by the endpoints of the experimental data, so that's why they're red dots. That's straightforward. And then every point in between these two positions, we need to use this R equation. So like I said, what you do, you put in the value of t, and you'll get out some coordinate which lies on the spline between these two data points. So let's go through and do that. And as I said before, each of the positions that you've evaluated through a spline, we mix together to produce some coordinate which is a mixture of all 4 of these points. Okay, so I'm just going to run through in steps of 0.1. So if you enter 0.1 into this equation, the result you get is the following: 2.247, 16.39. And then we're just going to run through and evaluate the equation R in steps of 0.1. I'll not read them out. And there we go. So that's the way the spline works. This is evaluating the steps of 0.1. If you want to have a nice finer curve, you can reduce that to 0.01, for example, or whatever you want. So that's the way you do it, and that's how you get your spline. Okay, so then once you've got one spline, you need to loop through and do this for every spline you have. So you need to go from t equals 0 to 1, but you need to do that for every spline you have. So in our case, we have 5, and you just keep going and filling up the graph with all of the splines. And that's how you do it, and that's how you evaluate the spline. So like I say, there's quite a few steps there, but if you're satisfied with not necessarily knowing all the details of how you come about this answer, it can be reasonably easily implemented. When it comes to actually using this within your, presumably you're going to need to use this within code, it's there are several ways you can use it. Once you have this relationship, you have all the variables stored. Once you've calibrated the data, you may, for example, wish to know what voltage corresponds to which power. So for example, T isn't very useful there. T is basically an intermediate step to evaluate a coordinate. So if, for example, you are very interested in the value of power at a voltage of 7.5, you may have to recursively look through R or something like that. It depends exactly your implementation, but that's one way of doing it. The important thing is that once you've carried out this procedure, you can continuously use your calibration data to basically fill in all the gaps which you didn't measure when you were carrying out calibration. So like I say, it is a very, very powerful tool, especially when you don't know the functional form. This is sort of something that a lot of people can run into this problem where you really need to know these points in between. You could just fit straight lines, but it's sometimes not as satisfactory to do that if the relationship between the two variables is complicated. Anyway, thank you so much for watching, and if you're interested in keeping up with more of the videos that I upload, just hit the subscribe button, and thanks so much for watching.